Organic chemistry is an exciting topic, and we will cover 14 modules on this topic. In the first module, you will be introduced to organic chemistry, with applications that ranges from medication and pesticides to plastics, fuels, fragrances, and many more. You will understand why carbon is so important for organic chemistry, and then we're going to look at definitions, single, double, and triple bonds, and you will learn more about functional groups. So let's start with the first definition. Organic molecules are molecules that contain carbon atoms. We consider carbon as the basic building block of all organic compounds. But what makes carbon so special? If we look at carbon on the periodic table, you will see that carbon has an atomic number of 6. This means that carbon has 6 protons and 6 electrons. And if you look at the atomic mass, carbon also has 6 neutrons. Carbon is in group 4 of the periodic table. This means that carbon will have a valency of 4. Valency of 4 means that carbon needs 4 electrons to complete its outer shell or energy level. The Aufbau diagram of carbon that we know looks like this, where 4 electrons are distributed in the outer p and s orbitals of carbon. But this makes it difficult for carbon, because carbon now has 2 electrons in this s orbital, 1 electron in each of these 2 p orbitals, so it can share these 2 p orbitals with other atoms, but no electron in the last p orbital, so it can do nothing with that p orbital. So, through different types of hybridization, carbon changes into an excited state, where new sp orbitals are formed with 1 electron in each of these sp orbitals. So carbon now has 4 orbitals with 1 electron in each, so it can share 4 orbitals with other atoms. You don't have to understand hybridization. What you have to know is that each carbon atom has 4 electrons to share with other atoms. And this is illustrated in the Lewis structure of carbon, where 4 electrons can be shared with other atoms. When these electrons are shared between carbon atoms, single bonds are possible where 1 orbital is shared between 2 carbon atoms. Double bonds are possible where 2 orbitals are shared between 2 carbon atoms. Triple bonds are possible where 3 orbitals are shared between 2 carbon atoms. But 4 bonds are not possible between 2 carbon atoms. On the right hand side are the Cooper structures of single, double, and triple bonds. These single, double, and triple bonds are drawn between the atoms that share the orbitals. The other bonds are not drawn at specific angles. They must just be drawn between the atoms that share those orbitals. We said that organic molecules are molecules that contain carbon atoms, and these carbon atoms can be bonded to hydrogen atoms. The carbons can also be bonded to oxygen, nitrogen, the halogens, phosphorus, and sulfur. But for the CAPS syllabus, we will focus on carbons that are bonded to hydrogens, oxygens, and the halogens. So you can forget about nitrogen, phosphorus, and sulfur for now. You will be introduced to different structures in organic chemistry. You will get to know carbon chains with different chain lengths depending on the amount of carbons in the chains. You will also get to know branches, and branches are attached to the carbon chains. You might also come across cyclic structures These structures are not in the syllabus, but you might see them in some of the textbooks and in the practical component. We have a few more definitions to look at. Homologous series is a series of organic compounds that can be described by the same general formula. So it's almost like a family name for molecules with the same general formula. So what is meant by the general formula? The general formula is a formula for a group of similar compounds. So for the homologous series of the alkenes, all the molecules have formulas with double the amount of hydrogens compared to the amount of carbons. For example, if there are 5 carbons in the molecule, there will be 10 hydrogens, or C3H6, or C10H20. All of these molecules will be part of the alkenes. You are used to the molecular formula of a molecule. The molecular formula indicates the types of atoms and the correct number of each in the molecule. For example, the molecular formula for butene is C4H8, which indicate to us that there are 4 carbons and 8 hydrogens in one molecule of butene. We will mainly use structural formulas to represent organic molecules. A structural formula shows which atoms are attached to which within a molecule, and we use chemical symbols to represent all the atoms and lines to represent all the bonds that hold these atoms together. An example is butene. So you can see that there are 4 carbon atoms in the structure of butene and 8 hydrogen atoms. And these atoms are bonded by single bonds and double bonds between the different atoms. We may also use a condensed structural formula. This is a formula that shows the way in which atoms are bonded together in the molecule, but does not show all the bond lines. So butene will be CH2, CH, CH2, CH3, because the first carbon is attached to 2 hydrogens, the second only to 1, the third to 2 again, and the last carbon to 3 hydrogens. You must know how to interpret these condensed structural formulas, but you may never use these formulas to answer any of the questions in the question paper. You will be instructed and they will expect you to use structural formulas to answer your questions, and you will be penalized if you use any of the condensed formulas. The definition for a functional group is a very popular question in the exams. A functional group is a bond or an atom or a group of atoms which determine the physical and the chemical properties of a group of organic compounds. For example, if a molecule only have carbon-hydrogen and carbon-carbon single bonds, you know that that molecule belongs to the homologous series of alkanes. If there is at least one carbon-carbon double bond, the molecule belongs to the alkenes. And if there's at least one carbon-carbon triple bond, you know that the molecule belongs to the alkanes. You must know the functional group of each homologous series. There are 4 important structures that you must be able to identify and name. The first one is a carbon that's bonded to an oxygen with a double bond. We call this a carbonyl group. Then we have a hydroxyl group. A hydroxyl group is a carbon that's bonded to an oxygen, and that oxygen must be bonded to another hydrogen. The third group is a combination of these two, where you have a carbonyl but also a hydroxyl on the same carbon, and we call this a carboxyl group. And the last one is called a formal group. And a formal group is a carbon that is bonded with a double bond to an oxygen, and then that same carbon must also be bonded to a hydrogen atom. Let's have a look at all the functional groups and general formulas for the homologous series included in the CAP syllabus. The first homologous series is the alkanes. Now, with the alkanes, an example of an alkane is ethane, and you can see that the name includes the postfix ane, the ane in the name. If you look at the general formula, there will be double the amount of hydrogens compared to the carbons plus another 2. So the general formula will be CnH2n plus 2. The functional group for the alkanes will be the single bonds between the carbons and hydrogens. So if they ask you to draw the structural formula of the functional group of an alkane, it will look like this. If they ask you to explain, you will say there are only carbon-hydrogen and carbon-carbon single bonds. For an alkene, the name of the molecule will have a postfix of ene. The general formula will have double the amount of hydrogens compared to the carbons, so it will be CnH2n. And if you look for the functional group of the alkenes, it will be a double bond between two carbons. So the functional group, if they ask you to draw the structural formula of it, will look like that, at least one double bond between two carbons. And then if they ask for an explanation, you will say that there must be at least one carbon-carbon double bond in the molecule. The name of an alkene must have the postfix YNE. For the general formula, there will be double the amount of hydrogens compared to the carbons minus 2. So the general formula for the alkenes will be CnH2n minus 2. And then for the structural formula of the functional group, there must be at least one triple bond between two carbon atoms. And an explanation of the functional group is at least one carbon-carbon triple bond. The fourth group is called the haloalkanes or the alkyl halides. And the name of one of the molecules of the haloalkanes must reveal one of the halogens in the name, and then the rest of the name will look similar to one of the alkanes. If we look at the general formula of the haloalkanes, you will see that there are double the amount of hydrogens compared to the carbons plus 1, and then there will also be at least one of the halogens in this general formula. So we indicate that with an X, and then you just show at the bottom that X can be any one of these halogens. If they ask you to draw a structural formula of the functional group of the haloalkanes, then you will draw a carbon that is attached by any halogen. So we again use an X to show that that X can be any one of the halogens. And if they ask you to describe the functional group of a haloalkane, you will say that there's a halogen atom bonded to a saturated carbon atom. The name of an alcohol always ends with an OL, and the general formula for an alcohol is always CnH2n plus 1, and then there must also be an OH. And the structural formula for the functional group of an alcohol is that carbon attached to an oxygen and the oxygen that's attached to a hydrogen. So it will look like that. And we call this a hydroxyl group bonded to a saturated carbon atom. A carboxylic acid will always end in oic acid, for example, ethanoic acid. So if you look at a molecule of ethanoic acid, you will find this special group of atoms, which we have a special name for. A carbon attached to two oxygens, where one of the oxygens is also attached to a hydrogen, we call a carboxyl group. So for the general formula of the carboxylic acids, there must be double the amount of hydrogens compared to the carbons, and there must be two oxygens. So the general formula will be CnH2n and then two oxygens, O2. For the functional group, if they ask you to draw the structure of a functional group for the carboxylic acids, you will just draw the carboxyl group, which is the carbon attached to two oxygens and that oxygen attached to another hydrogen. The next homologous series is called the esters. A name of an ester always consists of two words, and the second word end on an O8. If you look at the molecule of an ester, you will find an oxygen in the main chain of carbons. And adjacent to that oxygen, one of the carbons must have a double bond to a second oxygen. So the general formula for the esters look exactly the same as the general formula for the carboxylic acids. So it's double the amount of hydrogens compared to the carbons and two oxygens. The structural formula for the functional group of an ester will be the carbon with the oxygen and another carbon, and one of these carbons also bonded to a second oxygen. The aldehydes are not included in the IEB syllabus, but it is included in the CAPS syllabus. Now the name of an aldehyde ends on AL, and a molecule of an aldehyde will always have this formal group. Now a formal group consists of a carbonyl group, and that carbonyl group is also attached to a hydrogen. The general formula for the aldehydes is double the amount of hydrogens compared to the carbons and then one oxygen. And then the structural formula of the functional group for an aldehyde is the formal group. The last homologous series that we will cover is the ketones. And the name of a ketone will always end on an O-N-E. The molecule of a ketone will always have a carbonic group that's not on the first or the last carbon, because if it's on the first or the last carbon, it's not a ketone anymore, then it's an aldehyde. So the carbonic group must be somewhere in the middle of the chain. So the general formula for a ketone, again similar to that of the aldehydes, it's CnH2nO, and the functional group of a ketone will then be a carbonyl group that's bonded to two carbons. It cannot be on the first or the last carbon of a chain. Let's conclude this module with a few questions. The first question is to identify the homologous series where there's a hydroxyl group bonded to a carbon chain. So a hydroxyl group, remember hydroxyl group is a carbon bonded to an oxygen and a hydrogen. And we know that this is the functional group of the alcohols. Carbon-carbon double bonds. We know that the homologous series where there's at least one carbon-carbon double bond is called the alkenes. A carbonyl group bonded to a hydrogen atom at the end of a carbon chain. Alright, a carbonyl group is where you have a carbon bonded to an oxygen with a double bond, and when this carbonyl group is on the last carbon or the first carbon of a carbon chain, that carbon will also be bonded to a hydrogen, and then we call this a formal group, and the formal group is a functional group for the aldehydes. Write down the functional group for the following compound and write down the homologous series to which the compound belonged to. Right, so we can immediately see that there's a double bond between two carbons, and the double bond between two carbons is the functional group for the alkenes. When you study this molecule, it is the halogen that immediately catches your attention. So the functional group here will be the halogen, which can be any one of these halogens attached or bonded to a carbon. And we call this homologous series the haloalkanes or the alkyl halides. The next molecule has an oxygen in the carbon chain, and then one of the carbons adjacent to that oxygen is bonded to a second oxygen with a double bond, and we know that this functional group is the functional group of the esters. When you are asked to write down the homologous series of a compound that's given in its condensed formula, it's just easier to first draw the structure of that formula. So you will start from the left with the first carbon, and the first carbon is bonded to 3 hydrogens. The next carbon bonded to 2 hydrogens. Then you have a carbon bonded to 1 hydrogen, and the next carbon is also bonded to 1 hydrogen. It doesn't matter where you draw that hydrogen. And then the fifth carbon bonded to 2 hydrogens, and the last one bonded to 3 again. So if you start from the left and you make sure that each carbon is bonded to 4 other atoms, you will see that the first one have 4 bonds, the second one 4 bonds, but the third one and the fourth one only have 3 bonds each to other other atoms. So you have to include a double bond between those 2 carbons to make it 4 bonds on that carbon and 4 bonds on that carbon. And then the last 2, both of them have 4 bonds again. So a double bond is the functional group of the alkenes. We end this module with this last molecule, and because it's in a condensed formula, we first draw the structure of this formula again. So the first carbon bonded to 3 hydrogens, then we have a carbon bonded to 2 oxygens. So the first oxygen will be a carbonyl group, a carbon bonded to an oxygen with a double bond, and then that same carbon must be bonded to a second oxygen, and that oxygen bonded to a carbon which is bonded to 2 hydrogens, and then the last carbon also bonded to 3 hydrogens. Now the carbon bonded to 2 oxygens, where one of the oxygens is in the chain of carbons, is the functional group of the esters. If you are an educator that would like to inquire about the use of these PowerPoint slideshows in your classroom, you may contact me at lawsandwonders@gmail.com. Please indicate if this topic was useful to you or not, and subscribe to my YouTube channel in order to stay informed about the release of my most recent videos.